Hello, I'm Mathias Malandain from INRIA Rennes in France, and I will be taking the next 15 minutes or so to present our approach for handling multimode models and mode changes in Modelica. The paper is authored by Benveniste, Benoît Caillaud, and myself. Since 2012, the Modelica language makes it possible to design multimode models, where each mode is described by a different system of differential algebraic equations. This is a very valuable feature for industrial model designers. Unfortunately, it has also been the source of a lot of difficulties with Modelica tools ever since. Some meaningful models are not handled well by tools such as Modelica or Daimler. Division by zero exceptions occur during numerical simulations, in situations where the model itself is not at fault. These issues are related to mathematical properties of the underlying multimode DA system, such as its differentiation index that can vary between modes. However, we strongly advocate that it should be the task of the Modelica compilers to deal with these aspects, as they do with single-mode models. Instead of that, end users too often have to rely on experts, or even tool developers, who will painstakingly tweak the models so that they are correctly handled by the tools. These model transformations usually amount to performing index reduction by hand in some troublesome modes, which is an unwanted situation, as index reduction is one of the key roles of Modelica compilers. From the user's point of view, models that seem perfectly sound and physically meaningful may or may not be correctly handled by Modelica tools, as there's no simple characterization of problematic multimode models. We believe that this hinders the wider spreading of Modelica tools, which is why our works aim at providing algorithms for the correct compilation of multimode Modelica models. In the paper, we take a close look at two small but representative examples of multimode models that are not well handled by most Modelica tools. For this presentation, we will be mainly focusing on an idealized model of a clutch. This example will also be the leading example for the last talk of this session by Benveniste. We will explain why neither Daimler nor OpenModelica are able, at least for now, to correctly simulate this model, and we will show how our approach overcomes the current limitations of these tools. More precisely, we will start by presenting the model and showing how and why issues occur with these tools. As they are related to structural analysis, we will show how we revisit it so that both modes and mode changes are studied. The clutch model being impulsive at a mode change, we will also sketch the specific handling of this impulsive behavior. Before concluding, we will still say a few words about the cup and ball model, as it raises an interesting question that is not addressed by the clutch model. So let us start with the model of the idealized clutch with two shafts. It has four variables. Omega1 and omega2 are the angular velocities of the shafts, while tau1 and tau2 are the torques applied to them. On each side, you can see that the dynamics of the shafts are simply described by first-order differential equations on the angular velocities, where the coefficients J1 and J2 are the moments of inertia of the shafts. At the center, algebraic equations describing the junction of the shafts are provided. We assume that the system is subject to no external force. As a result, the torques are equal to zero as long as the shafts are not coupled. We will be referring to this mode as the released mode. In the engaged mode, that is, when the shafts are coupled, their velocities are equal, and by the law of action-reaction, the torques applied to them sum to zero. This last bit is of course true in both modes. However, this multimode DA model does not provide explicit laws for mode changes. In particular, as the coupling is assumed to be instantaneous, an impulsive mode change is expected when the clutch gets engaged. One can check this by computing by hand the command velocity of both shafts from the law of conservation of momentum. This value depends on the left limits of the angular velocities of the shafts before the coupling, so that variables omega1 and omega2 will be in general subject to an instantaneous shift in values. As a matter of fact, state-of-the-art tools are currently unable to handle this mode change. Both Daimler 2021 and OpenModelica 1.17.0 return a division by zero exception at the time when the clutch gets engaged. And this is actually a symptom of something even more profound. The structural analysis implemented in these tools is not fit for general multimode models. The very next talk in this session will dive a bit deeper into this, explaining how these algorithms omit mode dependencies and thus perform a wrong causalization of the equations. As such, it turns out that even adding the right reinitialization statements will not help in this specific case. Moreover, computing the restart conditions by hand becomes near impossible for larger models. Indeed, let us imagine a model of a multiple clutch. The model itself is easy to design in Modelica by instantiating several shaft components and local junctions. However, there is a combinatorial explosion of mode change models, as every possible engagement of two or several shafts has to be considered. As such, our approach was designed with the idea that mode change laws should be inferred by the compiler using a physics-agnostic process, and that both this analysis and the structural analysis of the modes themselves should be carried out in a unified framework. The proposed approach actually works for a large class of multimode models, including models in which events of mode changes may instantaneously trigger other events as long as such cascades of events are finite. We illustrate this approach on the simple clutch model. We can first perform standard index reduction in each mode. The index of this model is mode dependent. When gamma is true, that is when the clutch is engaged, equation E3 has to be differentiated once. On the contrary, when gamma is false, no equation has to be differentiated. However, this analysis tells us nothing about what happens at mode changes. Our goal would be to perform some kind of structural analysis that will also handle these mode changes. Sample time will do the trick, but it would bring forth problems related to either the faithfulness of the results or the complexity of the implementation. Fortunately, non-standard analysis provides us with the possibility of using infinitesimal time steps, which alleviates any concerns we might have had about accuracy. Let us see how this helps us with structural analysis. Let epsilon be any fixed infinitesimal time step. That is, epsilon is not equal to 0, but it is smaller than any non-negative real number. We define the forward shift of x of t as x of t plus epsilon. Then, by using a first-order Euler approximation with time step epsilon, we define an explicit relation between the derivative x prime and the forward shift x bullet. Anywhere x is differentiable, the second equation gives an approximation of the derivative up to an infinitesimal order. Note that one can also define backward shifts in a similar way. We now have two possible expressions for latent equations, as we can either differentiate an equation or shift it. These two expressions are actually equivalent from the point of view of structural analysis, but they have different meanings. Differentiations belong to continuous time, so that they will be used for the modes. Shifts, on the other hand, represent discrete steps in zero duration, so that they will help us describe instantaneous mode changes. The mode change when the clutch gets engaged is studied in this setting by taking into account both the last instant before the mode change, in blue, and the first instant of the engagement, in black. Note that for the latter, we keep the latent equation that was found during the analysis of long modes. The analysis of this system finds that it contains an overdetermined subsystem marked with stars here. This subsystem contains three equations with only two dependent variables. This result is found by a simple Dulmage-Mendelssohn decomposition of the system without any structural analysis in the DAE sense. To resolve this conflict, we state that the past cannot be undone. That is, the first two equations cannot be erased, as they are, quote-unquote, about things that have already happened. Then the only solution left is to remode the consistency equation in the new mode. In practice, we actually just postpone it for a single non-standard instant, as its forward-shifted version is still taken into account for the mode change. Now, by solving this system, we should get restart values for the torques and for the forward shifts of the angular velocities. As epsilon is infinitesimal, it would be tempting to directly set it to 0. However, this actually leads to problems. Let us see exactly why and give hints on what can be done to solve this issue. Here is the system of equations to be solved for the torques and for the forward shifts of the angular velocities ω1 and ω2. Let us just expand the first two equations. Once this system is solved, we may just take the forward shifted values of the velocities as restart values. However, if epsilon is set to 0, the system is actually structurally singular. The first three equations only involve the velocities, and the last equation only involves the torques. So let us come back to the original system and investigate further. The angular velocities are standard real numbers, and they will be divided by epsilon to get the values of the torques, so that the torques are infinitely large non-standard reals. This impulsive behavior is actually consistent with physical intuition, but it is inferred without any such reasoning. One possible solution is then to eliminate the torques from the system by simple substitutions. Solving the remaining equations yields the restart values for the velocities that were found by hand from the conservation of angular momentum. We worked on how to make such an analysis of mode changes fully automated, including the detection of impulsive variables. This will be the topic of the last talk in this session. Before concluding this talk, we will take a quick look at the cup and ball model, as it illustrates another aspect of our approach, namely the possible handling of transient modes. The basic model is a variant on the infamous pendulum model, except that instead of considering a rod of fixed length, we now deal with a rope that may or may not be straight. As a result, we have a complementarity condition involving the three variables of the model. The distance between the mass and the origin cannot be greater than the length of the rope. The tension in the rope is non-negative, and this tension can be different from zero only when the rope is straight. This system can be rewritten as a multimode DAE system by using a parameter S and a Boolean mode variable gamma. This introduces a logical numerical constraint between these two variables. We solve it by introducing a left limit in the definition of gamma. This model is structurally sound in all modes. Note, however, that the impact law isn't specified here. Two assumptions are actually possible for the cascade of modes that occurs when the rope gets straight. Either the rope remains straight for a positive duration and the impact is fully inelastic, or the rope is only straight for an infinitesimal instant and the impact is elastic. In the latter case, the straight mode is only reached for a single instant. This is a transient mode. In the inelastic case, we collect the equations for three instants, the last one before the mode change and the first two instants in the new mode. We actually have to take two instants instead of just one because second-order derivatives appear in the system. The analysis then finds out which latent equations have to be erased so that the restart values for all variables of interest can be computed. From this information, the rest of the study unfolds as for the clutch. The situation is very different in the elastic case. The equation system that has to be handled for the mode change is actually underdetermined. The restart values for the leading variables cannot be uniquely determined. As a result, clear diagnostics can be returned to the user. Additional information must be provided for this mode change. Let us conclude. We propose a method for the structural analysis of multimode DAE systems that handles both long modes and mode changes in a unified framework with a completely physics-agnostic approach. More information about the specific handling of possible impulses at mode changes will be provided in the last talk in this session. The way toward an automation of this process and its scaling on large systems is paved by our experimental tool ISAMDAE. This software performs the structural analysis of long modes of multimode DAE systems in an all modes at once fashion, that is, without enumerating all possible modes of the system. The very next talk will present a model transformation for Modelica models that is made possible by this multimode analysis. We are currently working on implementing the structural analysis of mode changes in a similar fashion. Thank you for your attention.